Now I'm having some technical problems, sir. I can't go it out. Let me see it later. No problem. Sure. Temperature scales. Okay. See in this one better. We are having the different types of the scales. Let me draw that one for you. Like say for example, this is the first scale. And this is your another scale. And this one is your third type of a scale. This one is your fourth type of a scale. Okay. And the points which are in the downward direction, these are known as of your ice point. And this one is known as of your boiling
Sir, we
point.
cannot see the screen, sir. We can only see the main page.
Okay, let me just check it out once. Are you able to see it better?
Yes, sir. Now we are able to see.
I don't know what is happening to this today. Are you able to see it better?
Yes, sir.
Chalo. So in the temperature scales better, the lower point is your ice point and upper point is known as of your boiling point for me. Just a minute. Boiling point are also called as of your vapor point bit. Are also called as of your vapor point. Okay, for all of them that is the same. Like say for example, if I take one this is Celsius scale, this will be your Kelvin scale, this one will be your Fahrenheit scale, and this one is your Reamer scale. The first scale which is in the syllabus is your Celsius scale beta. The next one is your Kelvin scale represented by K. The next one is your Fahrenheit scale, and third one is of your Reamer scale. Clear for everyone? For ice point means for the Celsius scale, the lower fixed point is the lowest point is 0 degrees centigrade and boiling point is your 100 degrees centigrade. For the Kelvin, it is your 273.15 Kelvin and upper point will be equal to your 373.15 Kelvin. Okay. And for the Fahrenheit, the lower fixed point is 32 degrees and upper point is nothing but of your 212 degree Fahrenheit. Clear, beta? And for the Reamer, it is 0 Reamer and above point is nothing but of your 80 R. Hello? Hello? సార్ ఇప్పుడు కాదు సార్ అది మళ్ళీ ఆల్రెడీ లేట్ అయింది అది ఎక్కడో ఉంది అది నేను వేరేది యూజ్ చేస్తున్నాను ప్రస్తుతానికి ఈ ఒక్కరోజు కానివ్వండి okay chalo so what are the different types of the temperature scales beta ice point above point is nothing but boiling and for the Kelvin the lower fixed point are we can say that if your ice point is called as of a 273 and upper point is your 373.15 Kelvin. For the Fahrenheit scale it is 32 degree Fahrenheit and this one is a 212 and for the Reamer scale this one will be equal to how much beta 0 and as well as of your 80. Okay, this one is known as of your Celsius scale. This one is your Kelvin scale and this one is your Fahrenheit scale and last one is nothing but of your Reamer scale. Clear for everyone beta?
Sir, this is only with respect to water, right?
Yeah,
sir?
this is only with respect to water. With respect to water only. Okay?
Okay.
Clear?
Yes, sir.
Now if I'm writing the conversion relation for this one beta. Conversion relation. See the conversion relation. we will be writing here always the reading of that one beta minus your ice point divided by your vapor point minus of your ice point must be equal to your constant. Must be equal to your constant. Clear? So conversion relation, what you are using beta? Reading divided by your reading minus of your what do you call that one? Ice point divided by your vapor point minus ice point. So IP is known as what beta here? IP is known as of your ice point, and VP is known as of your vapor point. VP is known as of your what? Vapor point. Is that clear beta?
Yes, sir.
Sure. I don't know, only I got one slide today. Okay. So in the temperature scales, the lower point for the Celsius scale is 0 degrees centigrade and upper fixed point is 100 degrees centigrade. For Kelvin, it is 273.15, and the higher point or boiling point or vapor point is 373.15. And for the Fahrenheit scale, the lower fixed point is 32 degree Fahrenheit and upper fixed point is 212. And for this one right now, Reaumur scale, lower fixed point is 0R and upper fixed point is 80R. Clear, beta? Now, how do you write the conversion factor? Reading of that given minus of your ionization point divided by your vapor point minus ionization, what do you call that, ice point, will be equal to your constant. Like say if I'm taking the Celsius scale, for Celsius scale we'll take as reading C, ice point is 0, vapor point will be equal to 100 minus this will be 0, that is equals to. For the other scale it is your F minus lower fixed point or ice point is 32 divided by this one is your 212 minus of your how much will be beta 32. For Kelvin scale, it will be equal to how much beta? K minus this one is 273.15 divided by this one is your 373.15 minus 273.15. That is equals to Reaumur scale. Reading of the Reaumur scale, I'll write as of your R minus lower point is nothing but 0 divided by vapor point is your 80 minus of your 0. Got an idea? Is that clear? Now see, if I am taking the relation between the Celsius and Fahrenheit, this will become for me C by your 100 is equals to your F minus of 32 divided by 212 minus 32 is how much beta?
180, sir.
So it will be your 180. So this 0 and this 0 will get cancelled. 2 5s are 10, 2 9s are 18. So this will become for me C by 5 is equals to F minus 32 divided by 9. So this is the relation between your Celsius scale and the Fahrenheit scale. So in the same way, I can write the value of your F from this one. So if I need to write the value of your F will become how much? F is equals to your 9 by 5 into your C plus of your 32. So if Celsius scale reading is given for you, so this will become for me 9C divided by 5 or 9 by 5 into C plus 32. That will be the reading in your Fahrenheit. Clear for everyone?
Okay.
Clear, beta? So this is a conversion factor you need to remember. Please try to take the screenshot because I'm having only one slide today. So I need to rub this one and write it again on the same part. So for the temperature scale, if I'm taking right now for this one, the upper point is known as vapor point and lower point is known as of your ice point. And for doing the problems during the relation, the scales, we're using this conversion relation, but actually we are having a lot of depth of analysis of that one, but that is not required. For need, you just remember this much. For conversion relation is always you try to remember reading minus of your ice point divided by your vapor point or steam point or boiling point minus of your ice point will be equal to your constant. Clear, beta? Clear up this one?
Yes, sir.
Clear up this one, everyone?
Yes, sir.
Chalo, very. Just a minute. It is getting shared, beta. Clear?
Yes, sir.
Chalo. Let us try to do one problem
Yes,
on
sir.
this one. Try to take a rough paper and try to do the problem with me. But write the problem there. A faulty thermometer is getting shade now.
Yes, sir.
So write this question better. A faulty thermometer reads freezing point, and boiling point of water as -5 degrees centigrade and 95 degrees centigrade respectively. Okay. What is the correct value? What is the correct value of temperature as it reads 60 degrees centigrade on faulty thermometer? On faulty thermometer. Okay, this is a given question for you. A faulty thermometer reads freezing point. That means I'm having the faulty thermometer. Let me draw a faulty thermometer. This one is your faulty thermometer. Okay, for the faulty thermometer, the freezing point is -5 degrees centigrade, and the boiling point of this one is how much for me? 95 degrees centigrade. Okay, so what is the correct value of the temperature as it reads 60 degrees on faulty? Okay, on this one, it is reading some 60 degrees centigrade. Okay, if I'm comparing with your Celsius scale, beta, with your Celsius scale, here the correct reading will be equal to how much for me? This is your correct scale. This is your faulty scale. Okay, and for the correct scale, the reading is 0 degrees centigrade. Upper is nothing but of your 100 degrees centigrade. So this reading here might be some X. I need this value of X. Now read the question once again. A faulty thermometer reads the freezing point. That means this is a faulty thermometer. Its reading freezing point is, our ice point is -5 degrees centigrade, and a higher temperature or the boiling point of this one is how much? 95 degrees centigrade. What is the correct value of the temperature as it reads 60 degrees on the faulty meter? So on this one, it is reading how much for me, beta? 50, isn't it? So it is reading how much for me? 60 degrees centigrade on the faulty thermometer. So what is that value is asking there? Can you try to give me the answer, beta, anyone? Shall I give the options for you? Okay, see the first option is 60 degrees centigrade. Next option is 65 degrees centigrade. Third one is your 64 degrees centigrade. And fourth one is 62 degrees centigrade. So anyone can try this question. This one is Celsius scale, na beta? On the Celsius scale, it is reading how much for me, beta? 60. So this is your 60 minus lower fixed point is nothing but -5.
Sir.
Yeah. Divided by how much for me? Very good, 65. And this one is how much for me? 95 minus this one is also your minus. That is equals to, reading on this one is, say for example, X minus lower fixed point is 0 divided by upper fixed point is 100. Sorry. So this will be equal to your 100. So this is your 100 minus this one is 0. So 60 minus of -5, this is 65 divided by 95 minus plus 10. So this will become for me 100. That is equals to X divided by 100. This 100 will get cancelled. So X will be equal to 65. Got an idea how to do the problem?
Yes, sir.
Chalo, very good. Clear, beta?
Yes, sir.
Sir, you are not audible.
Yes, beta. I'm just checking.
Okay, sir.
Is there a problem was with my power cut, so the system is a little bit hanging.
Okay, sir, no problem. I was thinking that I was not getting the class. That's why I was asking.
Okay. So I hope you got an idea how to do the conversion problems, beta. So let us try to go for the
Yes, sir.
next one. Chalo, next one is about your thermal expansion. Thermal expansion. So the basic thing what you need to remember is always for all the questions in this one, universal truth, distance between any 2 points, distance between any 2 points increases due to rise in temperature. Due to rise in temperature. So, okay. So what is the thing you need to remember? Distance between any 2 points will increases due to rise in temperature. Whatever may be the points you're taking, like say this is your plate. If you're taking the 2 holes right now, this distance I'm taking it as D. This one is as radius R1. This one as of radius R2. This is metal plate. If I'm heating it, R1 will increase, distance will increase, R2 will also increase. Okay, if there is a metal plate like this with inner radius R1 and outer radius R2, and this is totally a metal plate. If you are heating this one, R1 will increase, R2 will increase, R1 minus of your R2 will also increase, whichever is in higher, that will, sorry, R2 minus of your R1 will also increase. Clear, better? If the plate is with a hole and the triangular shape, and the distance between them is D, this one is say for example R1 and this one is your A. When you heat it, R1 will increase, side of the triangle will increase, and the distance between them also will increase. Is that point clear? Is that point clear? So what is the thing I'm telling you? Distance between any 2 points increases due to the rise in temperature. Clear? Whatever may be the given conditions, it will always increase with our respect to all the points basically. Okay? Sure. In our syllabus beta, we are having 3 types of your expansions, if you might have been remembered them. First one is known as linear expansion. First one is known as what? Linear expansion. The next one is known as of your superficial expansion. Superficial are also called as of your aerial expansion. Aerial expansion. Associated with your 2 dimensions. This is associated with your 1 dimensions. And third one is about your volume expansion. Third one is about your volume expansion. In volume expansion, this is associated with your 3 dimensions part. Okay. In linear expansion, what is the formula you remembered better? Whenever there is an expansion or when a rod is being increased or when a rod is being heated, The expansion in this one is delta L is equals to your original length L naught into your alpha into delta T. I hope you remember this formula. That means final increase in the length will be L final will be equal to your L naught into 1 plus alpha into your delta T. Alpha is known as what, beta? Coefficient of linear expansion. Alpha is known as what? Your coefficient of your linear expansion. Coefficient of your linear expansion. In the same way, for superficial expansion, change in area delta A will be equal to your A naught, we represented by letter beta into delta T. So final increase in the area will be equal to your A naught into 1 plus beta into your delta T, where beta is known as what, beta? Coefficient of, this one is known as of your coefficient of your areal expansion. Coefficient of your areal expansion. Okay. And third one is volume expansion associated with three-dimensional bodies. Change in volume will be equal to original volume into gamma into your delta T. Or else final volume will be equal to your V naught into 1 plus gamma into your delta T, where gamma is known as what, beta? Coefficient of, this one is known as of your coefficient of your volume expansion. Coefficient of your volume expansion. Is it clear, beta? So the first thing you need to remember in the thermal expansion is the distance between any 2 points. The distance between any 2 points increases due to the rise in your temperature. So in this one, we are having three different types of your expansions. One is linear expansion. Next one is areal expansion. Third one is volume expansion. Linear expansion is associated with one dimension. Superficial or areal expansion is associated with like 2 dimension like disc वगैरह, and volume expansion is associated with 3 dimensions body like a solid cone or sphere or something like this. Linear expansion, the best example is a wire. Whenever a wire is being increased, the change in the length is being found to be delta L is equals to your L naught into alpha into delta T, and final expansion in the length will be equal to L naught into 1 plus alpha into delta T. Alpha is known as of your coefficient of your linear expansion. Clear, beta? And in the same way, change in expansion in area delta A is equals to A naught into beta into delta T, where beta is known as of your coefficient of areal expansion. The same way, volume expansion represented by 3D, delta V is equals to V naught into gamma into delta T, where gamma is known as coefficient of volume expansion. Is that clear?
Sir, what is L naught, A naught, and B naught, sir?
L naught is your initial length, beta. L naught is your initial length of rod. Initial length of your rod. Like say, if this is your initial length, beta, isn't it? L naught. When you heat it, the length of the rod will increase. This is your L final. And from here to here, if he is asking, this will be the increase in the length. That is nothing but delta L. Got it? Got it, beta? Clear? Before expanding,
Yes, sir.
the length of the rod is how much for me? L naught. When you heat it, it is increasing to L final. And what is increase is asking means this delta L will represents me the increase.
Okay, sir.
Initial is like say 50 centimeter and final is like 60 centimeter. What is an increase you will take? 60 minus 50. That is 10 centimeter is your increase in the length. Clear?
Yes, sir.
So, can I rub this one, beta? Nandini?
Yes, sir. You can rub, sir.
Next one. Third point on this one. Effect of temperature on density. Effect of temperature on density. Okay, so what is the effect of your temperature on your density? Now see, basic density formula is what, beta, for me? Initial density will be equal to mass by initial volume. Okay, and final density after heating will be equal to mass is not going to change, volume is going to change, that will be your V final. That is equals to your M divided by V final will be equal to how much, beta? V initial into 1 plus gamma into your delta theta. Isn't it? That means final density will be equal to your initial density, because M by V initial can be written as of your rho I divided by 1 plus gamma into your delta theta. So this is one of the important formula you need to remember. final density is equals to your initial density divided by 1 plus gamma into your delta T. Okay. If gamma into your delta theta is much lesser than 1, okay, then I can write here final density will be equal to your initial density into 1 minus gamma into your delta T. This is the next formula you need to remember. Clear? This is applicable only if gamma into delta T is very much lesser than 1. Because why beta? Because when you take this one up, it will become something like this. 1 plus x to the power of n formula. I hope you remembered. If x value is very small, this will be 1 plus n into your x. So see here what is happening is rho final is equals to rho initial. If I take the term up, this will become for me 1 plus gamma into delta T to the power of minus 1. If I use this formula here right now to simplify this one, binomial expansion. Okay, so this will become for me rho final will be equal to your rho initial into 1 minus gamma into delta theta, because this minus 1 I am multiplying here.
+1 हो जाता है ये.
Isn't it? If here is right now plus, so here it will become minus. If here it is minus, then it will become for me plus.
Yes, sir, understood.
Okay, so that is the effect of your density on your temperature of this one. So effect of temperature on the density, how do you calculate the formula? Rho f is equals to rho initial divided by 1 plus gamma into delta t. If gamma into delta t is very lesser than 1, then rho final will be equal to your initial density into 1 minus gamma into delta t. Delta theta is your rise in temperature. This one and this one are one and the same beta. This one delta theta is nothing but what for me? Rise in temperature. Rise in temperature. This delta theta is also same beta. It's only representation change. That's it.
Yes.
The next one, fourth point. Expansion in cavities, or I can say gaps. Like railways track, there is a gap between the two rails, isn't it? Like say if this is your circular hole and there is a small hole somewhere here, and this is totally a solid like this. Okay, now see what is happening is when I heat it better, this is made up of coefficient of linear expansion alpha. The radius from here to here is, say for example, capital R. Okay, beta. Clear? If I consider this one as a disk and you are increasing its temperature by your delta theta, then R final increase in the radius of this one will be equal to your initial radius R into 1 plus alpha into delta T. And final area will be equal to how much for me? Pi into your R square into 1 plus 2 alpha into your delta theta. Isn't it? Because you know the relation between alpha, beta and gamma, beta. Alpha is to, beta is to, gamma is equal to how much for me? 1 is to, 2 is to, 3. Very important relation, beta. Relation between coefficient of linear expansion, areal expansion, and cubical expansion is how much for me? Alpha is to, beta is to, gamma is 1 is to, 2 is to, 3. If I'm considering this body as of your disk beta right now in this situation, then when you're increasing it by certain temperature or when you're heating it to a certain temperature, the final increase in the radius of that one is given by the formula initial radius R into 1 plus alpha into delta T. If there is an increase in the area, then A final will be equal to your initial area will be pi R square into 1 plus 2 alpha into delta T. Actually, we'll be writing here as beta. Okay. Now, if I consider this body as of your sphere beta, okay, then R final no doubt will be equal to your R into 1 plus alpha into delta T even for this one. But there will be increase in the volume. So final volume will be equal to 4 by 3 pi into your R cube into 1 plus gamma. Gamma is equals to 3 times of alpha into your delta theta. Okay, now beta is 2 times of alpha. Gamma is equals to 3 times of your alpha. This is a relation you need to remember between alpha, beta and gamma. So alpha is to beta is to gamma is 1 is to 2 is to 3. Beta is equals to 2 times of alpha and gamma is equals to 3 times of your alpha. Is that clear, beta?
Yes, sir.
Chalo. This one you tell me the answer. Like say, if there is a gap right now like this, and this is the distance between them, d. Okay. Now what is happening for this one? Can you tell me? How do you find that when you heat it, what is happening to the gap? Is it increasing or decreasing? When you heat this one, it will increase because it is expanding in outward direction. Na, beta? I told you. The first point itself, I told you. Whenever you are heating, generally you see that as if there is in heating, the gap will decrease. No, the gap will increase. The gap will increase. So this will become for me D final, because the expansion of the solid is in the outward direction, beta. Isn't it?
Yes, sir.
So D final will be equal to your initial distance D into 1 plus alpha into delta T. Clear?
Yes, sir.
So don't get confused with that one. So tell me the answer for this one. If I'm taking a plate like now like this, there is some plate and there are some 2 points in this one. Point A and this one is your point B. Okay. And distance between them is, say for example, some L. When you heat it, what happened to the final length, beta? Again, the distance between them will increase. So L final is equals to your L into 1 plus alpha into delta T. Can I write like this?
Yes, sir.
Isn't it? So effect of the temperature and density we got, expansion in the cavities. Whenever there is some cavity in any metallic body, that cavity radius will always increase. That increase in the radius is being calculated by the formula R final is equals to R into 1 plus of your alpha into delta theta, and increase in the area. Increase in your area will be equal to final area will be equal to initial area. Initial area is pi into your R square into 1 plus beta into delta T. Beta value is equals to 2 times of alpha into delta T. The same way, if I'm considering this one to be a sphere, R final will be equal to your R into 1 plus alpha into delta T, and V final will be equal to 4 by 3 pi R cube into 1 plus 3 alpha into delta T. Now see in this one, if there is a metallic sphere right now, sorry, there is a ring like this with a small gap D. If I'm heating it, if it is been heated with a temperature of delta T, the gap between them will increase. That gap, final increase in that gap is calculated with the formula D final is equals to initial distance into 1 plus alpha into delta T. Even if in the linear bodies, if between A and B, if the initial length is L, and if you are increasing it to a certain temperature of your delta T, the final increase in the length is given with the formula L final is equals to your L into 1 plus alpha into your delta T. Is that clear, beta?
Yes, sir.
Any doubt in this one?
No, sir.
Chalo. Clear of this one?
Yes.
Sure. Next point. Very, very important bit. Effect of temperature on pendulum clocks. On your pendulum clocks. Effect of your temperature on your pendulum clocks. Okay, let's see. This is your pendulum. And here there is a small ball which has been oscillating to and fro like this. This is the length of this one, say for example of your L. Okay, so in this one, in the SHM, we come a term called as of your seconds pendulum. What is a seconds pendulum, beta? For one oscillation of pendulum, clock shows 2 seconds. One oscillation means what, beta? Can anyone tell me? One oscillation means the body will start from here. The body will start from here, goes like this, come back to the mean position, mean to extreme, extreme to mean. This is one oscillation. So for one complete oscillation, of your pendulum, clock shows how much time, beta? 2 seconds. That is the reason we are calling the time period of that one to be equal to your seconds pendulum. For one oscillation, the pendulum is showing your 2 seconds of your time. Clear? Time period formula, beta? T is equals to 2 pi under root of your L divided by G. Okay, now see here. When temperature is increased, when temperature is being increased, length increases. Length increases. And clock becomes what, beta? Clock becomes slow, or it loses time. Or it loses time. Try to remember this condition. When temperature increases, length will increase. If length is increasing, clock will become slow. When clock is becoming slow, that means it is losing the time, isn't it? The same way, when temperature decreases, then what is happening to the length? The length also decreases. When length is decreasing, time period also decreases. Time period also decreases. Whereas in this one, what happens to the time period, beta? What happens to the time period? In this one, time period will increase. In this one, time period will decrease. That means there will be either it moves fast, or I can say that it gains time. Clear for everyone? Once again. Time period formula, T is equals to your 2 pi under root of your L by your G. Clear? Now, when temperature is being increased, beta, length of the pendulum increases. When length is increasing, time period is also increasing. So when time period is increasing, that means the clock becomes slow and it loses your time. Whereas when temperature is decreasing, beta, length will decrease, so time period will decrease. So when time period is decreasing, that means it is moving either fast, or we can say that either it is gaining time. Is it clear? So therefore, time lost or gained, time lost or gained is calculated with the formula half into alpha into your delta theta into your time period t. Is that clear, beta? Is that clear? Time period lost or gain, no need of derivation, beta. There is no use of doing that all derivations also, because ultimately final also you need to remember only this relation. If you need more derivation of that one, I can send you my link in which I have been done all the derivation by using the approximations, but I don't think so that will work out for you anyway for the NEET examination. If you're listening for the first time, then only it will be useful. Otherwise, for the repeaters, it is not much required. So the loss or gain in the time period is been calculated the formula half into alpha into your delta t. Is that clear? Any doubt in this one, beta?
No, sir.
Chalo. One more and very important point in this one only.
Sir, your T denotes the time period, no?
So small t here represents the time period. Okay. Delta theta is your temperature difference. Okay. Here also time period is represented by your T.
Yes, sir.
Okay. Next one. Thermal stress. Thermal stress. You see here, this is a rigid wall, beta. This is a rigid wall. In between this rigid wall, a small rod is being fixed like this, and linear expansion is not allowed. So when you heat it to red hot, so what is happening is the rod will slightly bend like this. You will see the expansion in the rod like this. This expansion in the rod, this bending of a rod is called as of your thermal stress. We know one formula, beta. Y is equals to your thermal stress. Thermal stress, elasticity mein we have done this one, divided by your thermal strain. Thermal strain. Okay, that means thermal stress will be equal to how much, beta? Thermal stress is equals to Y into your thermal strain. Y into your thermal strain. Strain means what, beta? Change in length by original length. Thermal stress means force by area, that is equals to Y into change in length divided by original length. Okay, as we know alpha is equals to delta L by your L into your delta theta. Therefore, delta L divided by L will be equal to alpha into delta theta. So this can be written as of your Y into alpha into your delta theta. So force formula will become how much for me? YA alpha into your rise in temperature delta theta. So this is your thermal force formula, And thermal stress is asking. So thermal stress will be equal to force by area, that is equals to Y into alpha into your delta. Clear, beta? Is that clear? Is that clear, beta? Effect of temperature on the pendulum clock. If the
Yes.
temperature is increasing, length increases, the clock will become slow or loses the time and the time period will increase. Whereas when the temperature is decreased, the length will decrease, time period will decrease, it will go fast or gain. Thermal stress, Y is equals to, Y is known as what, beta? Young's modulus. Y is known as what? Young's modulus. Y is known as of your Young's modulus. Young's modulus is equals to thermal stress divided by your thermal strain. Thermal stress divided by thermal strain. So thermal stress, if I'm bringing out, so it will be Young's modulus into thermal strain. So stress is nothing but force by area, that is Young's modulus into strain is change in length by original length. So change in length by original length by formula is how much for me? Alpha into delta T. Alpha is coefficient of linear expansion and delta T is your rise in your temperature. Is that clear for everyone? Chalo, next one and very important, one more point we need to remember, that is about your bimetallic strip. Bimetallic strip. What do you mean by bimetallic strip, beta? Combination of two different metals which have been fixed, which are being used as a thermostats in our iron boxes or something like this. These are two different metals, beta. So here there is one metal right now, and other side is made up of your another metal right now. Okay. And this is made up of, like, say, coefficient of linear expansion alpha 1. This one is made up of your alpha 2. And the thickness of this one is, say, for example, equal to your T. This one is your thickness T. Okay. So on heating, what is happening is right now for this one, beta, on heating, if alpha 1 is greater than alpha 2, alpha 1 is greater than alpha 2, the bending will be something like this. Alpha 1 will be on outer side like this. Clear, beta? This will be bending. This will form an arc of a circle like this. Okay, making an angle of your theta. This one is your radius r from here to here. Okay, so if alpha 1 is greater than alpha 2, so the alpha 1 will be on the outside. The alpha 1 will be on your outer side part of relation. So this will be your outer side alpha 1 and this will be your alpha 2 on the inner side. So this radius is being calculated with the formula r is equals to thickness T divided by your alpha 1 minus of your alpha 2 into your rise in temperature. This is your delta T. This is a standard formula which you need to remember. Radius of your bimetallic strip is equals to your thickness divided by your alpha 1 minus of your alpha 2. Alpha 1 minus of your alpha 2. Just a minute. It has been. Yeah. Okay. So this is the condition. On heating, the alpha 1 will be on the outer side and alpha 2 will be on the inner side. Any doubt in this one to anyone?
No, sir.
If alpha 2 is greater than beta, at that time what happens? If alpha 2 is greater than alpha 1, then I'll write here. If alpha 2 is greater than alpha 1, then this shape will become something like this. This will be this one. This will make an angle theta. This. Okay. So this will become for me alpha 2 and this will become for me alpha 1. Whichever is in larger beta, that will be on outer side. That you need to remember always. Okay, na?
Okay, sir.
For this one, how do you write the radius, beta? R is equals to thickness T divided by, here it is alpha 2 minus alpha 1 into your temperature difference delta theta. That will give me the answer for this. Clear?
Yes.
Sure. Sure. Expansion of liquids. We'll try to do it in the tomorrow and start doing the numericals based on this one beta. But all the nectar, whichever has been required in the solids, I have been done it. And very important in this one is of your this pendulum problems only beta, and bimetallics this direct step problems, and this thermal stress also very important. And relation between alpha, beta, and gamma is usually, we'll try to go for the working of this one in the tomorrow section of a class. Okay. Sure. Take care, beta. Bye.